Now, let's look at the third point, how probability theory explains microscopic motion. Let's study the movement patterns of molecules. If you observe a glass of water with naked eyes, you can hardly detect any movement. But magnified millions of times, the water reveals obvious granular structure, composed of densely packed individual molecules. At this scale, it becomes clear the water is far from static. Its molecules are in violent turmoil, resembling an extremely agitated crowd. Actually, all matter's molecules undergo constant random motion called thermal motion, not requiring external heating. Only at minus 273 degrees Celsius, absolute zero, would molecules become motionless. Common foods like pickles and salted eggs utilize sodium chloride molecules' constant movement through diffusion. Classic application of thermal motion. Since thermal motion is random, does that mean we can't calculate molecular trajectories? Mathematics works wonders. While it can't track every molecule's exact path, it can predict their most probable trajectories. Fascinatingly, molecular paths mirror a drunkard's wandering route. The drunkard's walk is a famous mathematical problem. Imagine a drunkard leaning against a lamppost, suddenly decides to wander randomly, taking steps in one direction, then changing course repeatedly. He keeps altering direction every few steps. After meandering through 100 turns, how far would he be from the lamppost? At first glance, each turn's unpredictability seems to defy solution. Now let's solve this rigorously using mathematics. Establish coordinate axes with the lamppost as origin. Applying simple Pythagorean theorem, we derive an infinitely long equation. For min turns, the equation requires summing from 1 to n. How to solve this? Here's where statistical approach shines. The drunkard's random directions create cancellation effects that intensify with more steps. So you'll find this infinitely long equation simplifies to an astonishingly simple result after reorganization. After 9 turns, the drunkard's most probable distance from the lamppost equals the average step length multiplied by the square root of n. For example, with 1 meter steps, after 100 turns, 1 times square root of 100 equals 10 meters. More turns mean longer duration and more precise calculations. Now replace drunkards with molecules. Imagine observing purple potassium permanganate diffusing in water. Each permanganate molecule acts like miniature drunkards, constantly bumped and redirected by water molecules. These molecules experience trillions of collisions and turns per second, moving near hundredths of an inch each step. Using our formula, it would take 10,000 seconds, nearly 3 hours, for purple molecules to diffuse 100 times minus just 1 inch. The life experience tells us diffusion is slow, hence stirring coffee to dissolve sugar faster. Yet molecules move at 576 kilometers per hour at room temperature, faster than China's 350 kilometers per hour Fuqing bullet trains. This probability formula perfectly explains why such violent motion appears calm macroscopically. Consider sunlight. 8 minutes from sun surface to Earth, but 50 centuries from solar core to surface. This starkly illustrates diffusion's incredible slowness. With few particles, we can only make probabilistic estimates. But with billions of molecules, strict diffusion laws emerge. Transition from uncertainty to maximum probability. The second law of thermodynamics, or entropy law. Entropy represents disorder and chaos. In an isolated system, any spontaneous change increases entropy. When entropy reaches maximum, the system achieves equilibrium. Like when arranging mahjong tiles in a neat wall, entropy is low. The entropy remains low during tile shuffling. When adding milk to coffee, initial separation gives way to mixing over time. This process shows entropy increasing, irreversible without external intervention. The sandcastle in desert soon collapses to disorder under wind, but no wind can reconstruct the original castle from scattered sand. Just as broken glass can't self-repair, this law explains y times arrow points unidirectionally. Now, let's transition from micro to macro. Fourth question, using parallax displacement to measure the cosmos. Mathematics has countless applications in cosmic studies. Today, we'll explore fundamental size measurements, how math helps understand Earth, solar system, and galaxy dimensions. When humans first realized Earth's spherical nature, measuring its size became imperative. In 3rd century BC, Eratosthenes learned Sienese vertical noon shadows during summer solstice differed from Alexandria's 7-degree angle. This inspired his calculation 7-degree difference equals 1/50th of Earth's circumference. By extending lines from Earth's center to both cities, he determined circumference as 50 times their distance. Eratosthenes finally calculated Earth's circumference as 40,000 kilometers, remarkably close to today's precise measurement of 40,076 kilometers, demonstrating astonishing accuracy for 2,000 years ago. The true significance of Earth's first measurement lies not in its precision, but in revealing our planet's immense scale. If Earth is this vast, how enormous must the cosmos beyond be? Thus emerged astronomy's fundamental question: Earth-Sun distance, the key to understanding cosmic dimensions. Scientists developed the parallax method to measure this cosmic distance. Displacement. The principle is simple. Try threading a needle with one eye closed to experience it yourself. With monocolor vision, you'll struggle aligning thread and needle. Depth perception fails without dual perspectives. Monocular vision creates angular disparity. Our neural system calculates distance from this parallax effect. This optical phenomenon is called parallax displacement. We replicate this by positioning telescopes at Earth's extremities, like cosmic eyes measuring solar angles. But solar distance requires rare celestial events like Venus transits for accurate measurement. First calculate Venus's parallax, then geometrically derive Earth-Sun distance. In 1761, astronomers worldwide competed like Olympic athletes, deploying elite teams to over 100 global locations. This international effort determined 133 million kilometers Earth-Sun distance, mapping solar system scale while propelling humanity towards stellar exploration. Parallax remains applicable, but Earth's diameter proves insufficient for measurable stellar parallax against cosmic vastness. Immovative suggestion. Solution emerges. Use Earth's orbital diameter as measurement baseline for stellar distances. Measure stellar parallax from Earth's orbital extremes, perihelion in January and aphelion in July. Thus, scientists extended their ruler beyond solar system, successfully measuring 61 Cygnus distance. This star lies 690,000 times farther than our sun. But parallax methods limit caps at 400 light years. Beyond that, angles become undetectable. Enter Cepheid variables, cosmic standard candles. Cepheid comes from the constellation Cepheus. The name's second character, Fu, means father in Chinese. In 18th century England, a deaf-mute youth with exceptional vision discovered stars pulsating rhythmically like heartbeats. These pulsating stars became known as Cepheid variables. Though passing at 22, this remarkable youth gifted humanity a new cosmic measuring tool. Scientists discovered mathematical relationship between Cepheids' luminosity and pulsation periods. Measure pulsation period, determine absolute brightness, calculate distance via inverse square law. Excited astronomers found Cepheids abundant in star clusters. Thus, measuring galactic scale distances became feasible. Crucially, Cepheids in other galaxies revealed those galaxies' distances. Milky Way's diameter, 160,000 light years. Andromeda's distance, 2.54 million light years. Current observable universe spans at least 92 billion light years in diameter. Not literal edge, but finite, unbounded space. Recall our curved space discussion. Remember space curvature from part 2? Our universe resembles a self-contained sphere. Spacefarers traveling straight would return home. In conclusion, we've explored 4 mathematical tools: imaginary numbers, triangle angles, probability theory, and parallax. These tools propelled developments in special relativity, general relativity, the second law of thermodynamics, and cosmic measurement. Mathematics stands as fundamental bedrock for scientific progress. It grants us enhanced perception through deeper conceptual frameworks, expanding exploration boundaries. From 1 to infinity symbolizes mathematical progression and scientific depth expansion. Humanity's unknown cosmic frontiers remain infinitely vast. Yet each step brings its joy, even facing endless truth. This concludes our journey through 1, 2, 3, infinity. Find reading notes below. Until tomorrow,